Morning, everyone. Welcome to Lecture 15. A few announcements, and I always have trouble with this. Here we go. There is lab today and tomorrow. Here is what will happen in lab, and probably from now on until the end of term, there will some portion of lab will be devoted to what we are calling a discussion worksheet. So that's a bunch of problems. This week is going to be on probability theory. I sent the GSIs some problems that I want them to do, and they have come up with some problems. Please note the word discussion. This worksheet is not for you to work on silently. It's for you to talk to other people about and argue about. All right? So it's going to be a portion of lab that is going to be about the ideas. And then, of course, the remainder of the lab is going to be devoted to your finishing part 3 of the project, which is due in just under a week now. No homework is due on Thursday, but there will be homework assigned on Friday. You've known this for some time. I hate to use the M word. It's coming up. Just over 2 weeks away. No computers, no calculators. So what is going to be on the midterm? All of those questions, such as, what do you think of this interpretation? What does this result mean? If you want the average over all households, what calculation would you do compared to if you want the average over all people? Does this histogram look like that one, or does it look like this other one? What do you think? I'm going to describe 3 histograms, right? So, how do you figure out how to do those problems? You go through your homeworks. Above all, you go through the textbook. That's where the concepts are. You have had a very code-focused few weeks. But all the discussions are in the textbook. I would suggest that you start reading it now. The time when I expect students to read a textbook is in between the lecture and the corresponding homework. So you have gone to lecture, you have a pretty good sense of what's going on, but then you are missing the details. Right? So you go back to the textbook and you get the details and you read the analyses and the interpretations over again and say, does this make sense to me? If not, I better talk to somebody. All right. So that is that's the plan for the next couple of weeks. Questions? Anybody? Yeah. Will we be releasing any previous midterms? So the answer to that is yes and no. We will be releasing questions that help you practice for the midterm. The reason we will not be releasing previous midterms is that the sequence is different this time. So if I released a previous midterm, I would freak out half my class because you wouldn't be able to do a bunch of the problems. And they wouldn't be able to do a bunch of the problems that we are going to ask you. More questions? Yeah. No, you do not. You need something to write with, preferably something to erase with. Unless you think you're not going to make a mistake at all. And you're very engaged and wonderful minds. That's what you need. Yes? Will we be hosting review sessions? So the lecture before the midterm, I will be doing some review here. We are not going to be, there's going to be plenty of review. The homeworks and so on are all going to make you go back over old materials. So we don't feel we need to have a special review session. You need to review. All right? And I don't have a way to make that shorter. So we will go through a problem so that you have practice doing problems that are short. But the review needs to start with you, and you should please start summarizing what you don't remember. Now, what we will hand out early is we will give you a sheet on the midterm that goes through the methods and the syntax. So you don't have to remember exactly which order the arguments come in and so on and so forth. That sheet will be given to you at the midterm, but we'll also give it to you a couple of days early so that you can see what's going to be on that, and then you'll see, oh, wait a minute, they're not going to give me this on the sheet, so I better learn that. That might be helpful. Okay? All right. I'd like to get started with where we were last time, and where we just begun. We'd done a discussion of how to calculate exact probabilities in fairly small problems, a few rolls of a die, a few tosses of a coin, and so on. And we were talking about large samples and sampling in particular, and one point I made at the end of lecture is you've been sampling all along. you've just been taking deterministic samples where there is no randomness involved. So you've used take to get rows of a table, that is, extract individuals from a population. You've used where to extract individuals from a population. But what we are going to be interested in is random samples, formerly known as probability samples. And here is what a probability sample is. To have a probability sample, you have to know what your population is that you're sampling from. And then you have to know ahead of time, for each group in the population, what is the chance that they're going to enter the sample. And so I'm going to... there it is on the slide. Before the sample is drawn, you have to be able to use the rules of probability to calculate the chance with which each subset is in the sample. And it is a very important note that not all individuals and not all subsets have to have equal chance. You can have unequal chance, you just have to know what the chances are. Then by using the rules of probability, you can account for whatever biases or otherwise are introduced by the unequal chance. But not knowing the chance ahead of time is a problem. And so I want to take you through one example of a probability sample. Actually, no, I'm not going to go to my demo yet. I'm going to go to this probability sample, and I want to take a look. So I've got a population of 3 individuals, A, B, and C, and I'm going to take a sample of size 2, and I have a bizarre sampling scheme. I am certain to take A, and then I will choose between B and C by tossing a coin. Okay? So this is a sampling scheme, and we are going to judge whether it is a probability sample. So the first thing we have to do is to note what are all the possible samples. I think all the possible samples are A, B, AC, and BC. You agree? A sample is a subset. Right? So AC is the same as CA. Okay. And so the question is, what is the chance of each of those sets? The chance of AB is what? Well, I got to get A. The chance of that is half. Once that's happened, I've got to get B. How do I get B? If the coin lands B's way, right? So 1 times a half is a half. So also, AC is 1 times a half is a half. BC you cannot get because you're going to pick one of B and C. Yep? What I'd like to do is I'd like to go through the probability calculation, right? Just formally. So I've got to get B and I've got to get C. What is the chance that I get B? 1/2. Yes? Now what do I do? What does my rule tell me to do from last time? I need to multiply by something. Yeah. Yes, there is a man who will go far. Multiply by the chance that you get B given that you get C given that you already got B. Yes? What is that chance? That chance is 0. All right, so that 0 is equal to 1/2 times 0 by the multiplication rule. All right, so this is a perfectly good probability sample. It's a little weird, but we can figure out what you expect from estimates based on a sample like this. What I'd like to do now is actually do the demo that is promised here. And so this is where we ended up at the end of last time. We had 2 deterministic samples, one using take and one using where, from this data set like right here. And I believe I've read it all in. So this is our movies data set. What I'm going to do is I am going to describe what is called a systematic sample. Okay? So not all samples consist of throwing your names into the population, throwing your hands into the population, just pulling out a bunch. There are various schemes that you can come up with. A standard one is a systematic sample, and this says, just get a beginning range, and I chose 0 through 9 because that's what my table shows me. Pick one of those at random, okay, and then take every 10th one. All right, so you don't have to do it in tens. You could pick one of the first 3 at random and then take every 15th one if you wish. But the scheme that we're going to do is pick one of these guys at random and then take every 10th one. And so, well, we can write... I have no idea. Oh, this is where I am. Okay. So here's the code. The starting point is np.random choice of range 0 through 9. And then we're going to take that starting point and every 10th one. Questions about the code? Questions about where it ends up? What's the last one you can take? What's the last index you can take? On any table, what is the biggest index you can take? The length minus 1, right? And that is ensured by going up to num rows here, because Python will stop right before that. So you will go to the start and you will take every 10th one until you hit the end. And so I'm going to run this. And so look at the indices. The random one that was chosen was 4, and then we got every 10th one. Do you see the indices all ending in 4? And so if I run it again, this time pick the index 9, and so it's everything ending in 9. All clear? All right. What I would like you to do is talk to your neighbors. Is this a probability sample? And if so, can we say anything about the chances with which the different groups get in? Go. All right, so let's try to work this through. To decide whether something is a probability sample, you have to think of all possible subsets and see whether you can figure out the chance that they get in, right? So what sizes of subsets are you going to be looking at? What's the size of your sample here? You can see 10, and then there's 10 rows omitted. Yep. There's a sample of size 20. Why? Because you have 200 total. And you're taking every 10, essentially. Right? So you have a sample of size 20. So what groups do you have to think about? Actually, lots of different groups. Because there are many, many groups of size 20 that you could pick from your 200. Yes? What about, let's just go back and look at, so this is the first 10 and the next 20. How about these first 20? All right, what is the chance that we get these? 0. Okay, so the vast majority of sets have probability 0. That's a perfectly good probability. Which are the only sets that are possible? The only sets that are possible are some start and then go in tens, right? So successive values are separated by 10. Those are the only ones that are possible, yes? Can you figure out the chance of this one, for example? What's random? 1 in 10, because the only thing that's random is the starting point. Right after that, everything is determined. So picking index 9 out of indices 0 through 9, the chance of that is 1 in 10. So each of these subsets have chance 1 in 10, and every other subset has chance 0. Okay, now you can see that in more complicated sampling schemes, you will have to do more careful calculations of probability. And we're not going to go there. I just want you to have some sense of what it means to take a probability sample. The ones that are classic that you will be doing over and over again is write the names of everybody on a ticket and then put the tickets in a box, shuffle, and pick at random, either with replacement or without replacement. And those have the property that all subsets are possible and all subsets of the same size have the same probability. Right? So those are the easy ones to analyze, but there are many others possible. Here is something that is not a random sample. If you stand at a street corner and take the first 10 people that pass by, you might think to yourself, well, I don't know who's passing by, it's totally random. Okay, perhaps in some colloquial sense of the word random, but that is not a random sample. Because you don't know who's going to pass by, you don't know what is the population of people who's going to pass by, and you certainly cannot say ahead of time, for each member of that hypothetical population, what is the chance with which they pass by. You can't say what is the chance with which any 10 pass by. So be careful, these are called samples of convenience for a reason. It's very convenient to stand at a street corner and get 10 people. It doesn't give you a random sample. The point is that you can't do any calculations based on these, right? Because you don't know the chances with which different elements get into the population. Okay, so we are going to be focused on random sampling for now with replacement. We will do some without replacement sampling, and you would think that, without replacement sampling is a little more natural. However, you will see in this course that with replacement sampling is a key to a great deal of inference. So we're going to be doing a lot of with replacement sampling from populations. All right, so I want you to start thinking about random quantities. And the example that we're going to start with is a very simple one. I want you to think of the number of spots on one roll of a die. This is a random quantity, and it has a bunch of possible values. What are the possible values, please? 1 through 6. A probability distribution consists of all the possible values and all the probabilities of those values. So this is a very simple distribution. The values are 1, 2, 3, 4, 5, 6, and each probability is 1/6. It tells you how the total probability of 1 is distributed over the different possible values. And we are going to look at some probability distributions and other kinds of distributions as well. The one thing to note is that you can think about probability distributions without ever having run an experiment. You just told me the probability distribution of one roll of a die. We didn't actually roll any dice, did we? So the probability distribution is a theoretical mathematical object, which we can visualize. You don't actually have to do any simulation. Okay, so now let me move to running a couple cells. I'm going to need a roulette wheel later, I hope. Okay, here we go. Here's a die. All right, so that has all of those faces, and here is a histogram. And there is your classic uniform distribution, a flat-topped histogram, right? No change. I want you to notice a bunch of things to do with the histogram, and this is my way of reviewing histograms with you. All right, notice that the bins stretch across an integer, a half on either side, but you can't actually get 2.3 spots, can you? Or 4.1 spots. So this visualization is actually smearing the probability of 1/6 over a bar. The actual action is right here at the integers. When you have data whose consecutive values are separated by fixed amounts, like this, everything separated by 1, the data are called discrete. We will frequently be drawing discrete histograms with the bars centered on the values, not just as a matter of convention, but for important use later when we start putting smooth curves over these histograms that have bars. All right, so when you look at a histogram, look always at the horizontal axis first. Notice that all the action is at the integers, but the probability is being spread out. And now, what is a unit here? From here to here, the width of the bin is how much? From here, the width of each bin is 1. Here you have the height is percent per unit is 16 and a bit. Yep. What's the area of the bar? It's this 16 and a bit percent per unit times 1 unit. That's that 16 and a bit percent. Yes? And where is that 16 and a bit percent coming from? 1/6. This 16.6666666, etc. That's what that is. Right? So we remember how to read this histogram. And this, we didn't have to roll any dice to come up with this. What we would like to do is to see what this histogram has to do with actually rolling dice. So what we're going to do is we are going to roll dice. And for this, we have to be able to pick at random with replacement from the rows of this table. The method that does that is called sample. Here is what sample does. If you use the method on the table dice, it will sample rows of this table at random by default with replacement. Is that a good model for rolling a die here? Yes, because each time you are sampling from the numbers 1 through 6. It samples at random by default with replacement, and you have to tell it how many times you want to sample. So if we want to roll 10 dice, the call is simply die.sample 10 times. And here are the 10 rolls that we got. And if I run it again, I get a different set, and if I run it again, I get a different set. No surprise to you at all, right? Okay, so now you have two methods of drawing things at random. If you have an array from which you want to draw, what is the method? np.random.choice. If you have a table where each row is an individual and you want to sample individuals, what is the method? .sample, table.sample. All right, so they operate on different objects and they return, this one returns a table, the other one returns an array. Yes? For the bins for my histograms, because I wanted to draw the bins centered on the values, the bin has to go from 0.5 to 1.5, right? And I put a 6.6 here because I know it's going to go up to 6.5 and then just stop there.
So if you did it, do you have to make sure that they're centered, or would you have the same? Would you have come to the same result using 0?
I would not. I will show you. The question is, what if I had not used these bins? What would the histogram have looked like?
If your range had been from 0 to 7, not like 0 to 10.
I am not understanding your question. Say again. Oh, I could have done 7 here, sure. I could have done 7. You'd have got a bunch of empty bins, but it doesn't matter. All right. So what I would like to do is now I would like to look at a histogram of these numbers. So we've got these 10 numbers. I'd like to draw a histogram of those numbers. And now you know what we're going to do. We're going to do 100 numbers and then 1,000 numbers and so on. And therefore, we define a little function that draws what is called an empirical histogram. So what does empirical mean? Empirical means observed. Empirical distributions are based on observations and typically from repetitions of an experiment over and over again. And they have on the horizontal axis, all the values that you have observed, and the areas are the proportions of the repetitions that produced each one. So empirical, based on observations, probability is a theoretical distribution. Okay, so therefore, my function is called die. This is because I'm going to use a die, empirical histogram. This is the number of repetitions. So in this case, it was 10. So what it does is it samples, and then it draws, so it will get a table just like this. And then it draws a histogram of the tables using the same bins that we have used before so that we can compare one histogram with another. All okay? All right, so there's your function. I'm not at United Airlines yet. Okay, so die empirical histogram. Let's do a histogram. So what it did was it rolled a die 10 times and drew a histogram of those 10 numbers. That's what it got. Does it look like this? It does not. Message 1. If you have a small number of repetitions, your empirical distribution need not look like the probability distribution. Right? When you have a small number of repetitions, the empirical distribution is quite variable. Increase the number of repetitions and getting there. The theoretical probabilities look like this. If you increase the number of repetitions to 100, you're getting something that looks like that. If you increase to 1,000, much better. And 10,000, hardly distinguishable at all. Okay. And what you have seen is something that is a consequence of what is colloquially known as the law of averages. As you keep repeating an experiment independently and under identical conditions, the proportion of times something happens gets closer to the actual probability of that event happening. So the proportion of times you get a 3 gets closer to this proportion of 1/6. Okay, so lots of parts to the statement. All of the parts are important, so please let's take a look. So law of average is based on many repetitions of a chance experiment under the same conditions. Each repetition ignores what has happened all around it. In such a situation, if you look at the proportion of times something happens, that proportion gets closer to the actual probability that that happens. And our example has been, as you increase the number of rolls, the proportion of times you see 5 spots gets closer and closer to 1/6. You put this together, so this is a statement for 5 spots, but the same thing is true for 1 spot and 2 spots and 3 spots and so on. So what you have as a result is that the entire empirical distribution, that empirical histogram, begins to look like the probability histogram that you started with as you draw more and more times. And the same thing is true if you actually draw from a large population of individuals. And for this, I have a data set from the Bureau of Transportation Statistics, which has publicly available data on every flight out of every airport in the United States. So these are last summer, not this past summer, but the summer of 2015, June through August of 2015, every United domestic flight out of SFO. And there were 13,825 of them. So maybe a few are missing, but these are the ones that were available on the website. And the variables are the date of the flight number, the destination airport, that's Honolulu, and the amount of flight delay. The flight delay is measured in minutes. And so I thought it would be interesting to look at how often United flights are delayed, because the airline comes in for quite a lot of bashing, and, well, we should look at the data. And it's a good way to start sampling from a large population. So I'll be considering this as my population, and I'll be taking samples to see the relation between sample and population. Okay. Interesting question. What was the minimum delay? Please look, minus 16 minutes. That flight left early. Right? Not many do that, but that one did. Maximum delay, everybody's interested in that. 580 minutes. Well, I don't know at what point do they cancel the flight, right? And this one is just called a delay. So anyway, but most of them look like what? Well, I drew a histogram. So most of them are in the 0 to 200 range, 0 to 150 roughly, right? There's a few that left early. Everything to the left of 0 left early. And then, there are some very long delays, but there really aren't that many of them. Okay. Now, somebody's going to ask me, how did you choose these bins? I chose those bins because I messed around with the data, and I saw where the data lay. And so I have bins going every 10 from minus 20 to 300, and then just another bin from 300 to 600. Okay? And what I'd love to do is I would love to just look at this without this long, barely visible tail. So I'm just... so I would like to look at just this portion because this portion, there isn't a lot there, and it's very hard to see this picture all scrunched up. So one thing that's important is to see what proportion were actually in this range. And do you agree that that code will get it for me? Where the delays are above 200, how many rows relative to the total number of rows? Yeah, that's the proportion thing that you've been doing in your project. The proportion of tax returns that come from zip codes that have farmers in them and so on. Exactly the same code. And so what was that proportion? That proportion was pretty small. It was 0.8%. Right? That was very, very small. So just for visualization, I am just going to go up to 200. The table still has all the data, but we're zooming in on the main action in the histogram. And I want to be really clear that we understand what the histogram's doing. You see this? This is just below 3. You agree? Okay. The units are minutes. This says 3% per minute. How many minutes are there in this bar? 10. This goes from 0 to 10. How do you know that? From here. Yep. So there are 10 minutes. There is 3% per minute. Therefore, in this bar, what percent of the flights are there? 30. There's 3% for each minute. There are 10 minutes, and therefore there's 30% total in the bar. Yep. Area equals height times width. Okay. Let's just confirm that. If you calculate what percent of the delays are between 0 and 10, then the proportion that you get is 29.35. Okay, just below 30, that's what we said. All right? So this is the same old histogram, no changes to histograms, whatever. What we're going to do now is we're going to sample from this and look at what the sampled delays look like. Now, one of the things to keep in mind is if you actually have the entire population, you are unlikely to want to take a sample. You're just going to work with the whole population. The reason for doing this is an exercise for us to see whether random samples resemble populations or not. If they do, we're onto a good thing, because then you can use a random sample as a stand-in for the population. So that's our hope. So what we'd like to do is to get an empirical histogram of delays from a random sample of size n. So we take our table and we do dot sample n at this stage. Here's my cursor right here, right? Please look to the left of the cursor. At that stage, what do you have? You have a table. It has how many rows? It has n rows, whatever was your sample size. Yes? Those rows have been selected from where? From the united table, that huge table. Yes? In what manner? At random with replacement. That's the default. You have a table. So now any old table, you use table methods. You select the delays and you draw a histogram according to our old bins. And so you've defined your function. And now I want to draw the empirical histogram of just 10 flights selected. The delays of 10 flights selected, you can see that it's kind of trying to look like this, but it's not really getting there, is it? And where is the biggest problem? The biggest problem are in these rare events. Right? When you have a small sample, you just don't pick them up. And so if we increase sample size, better. It's trying to look like that. Sample size of 100, it looks more like that. You pick up more of these rare things. Sample size of 1,000. Better still. Sample size, so that we don't have to wait too long. Sample size of 5,000. Your sample looks like that, and your population look like that. Sample, population. Sample, population. Look similar? Excellent question. So I ran a sample size of 100 once. What if I just kept the sample size constant and ran it again? I should get a different sample, right? So I should get a different histogram. Largely continues to have the same problem, right? If I take instead the sample of size 5,000, like that, run it again, like that. Run it again. You can see it stabilizes. Yeah? So the larger your sample, provided the sample is drawn at random, the larger the sample, the more it resembles the actual population with high probability. All right. So thus far, everybody's sitting there going, yeah, I kind of know this. What I don't know is the code. Great. I'm very glad that you know this, because we are going to start using it soon to do inference. But today, what I would love to do is I would love to actually start looking not at entire samples, but at numbers that we compute based on samples. And so I want to go back to probability theory gambling. If you decide that you're going to play roulette over and over again, then you will have your list of wins and losses. At the end of the day, what you're interested in is the total. Yes, net, what do I come away with? And so you are not interested in so much in the details of the entire distribution, but just on that one quantity that you can compute. So what we're going to do is we're going to now draw samples and then compute a quantity and do that over and over again and see what we can say about those quantities. Is that a question? Yes.
Back to the first probability sample example that you gave, the picking every 10th after you pick your random integer.
Okay, the systematic sample, can I please come back to that offline? Thank you, because it's really, this is not the flow right now. Sorry. Okay, I will, catch me after class. All right, so what I want to do now is I have a nice amount of time. So we have, if the sample size is large, then the empirical distribution of the sample resembles the distribution of the population with high probability. By the way, I would like you to look at that statement. You've seen I've broken it up into bits. Every bit is crucial. So when you write an answer and you ask for a regrade saying, well, I wrote pretty much the same thing, if you're missing one of these bits, it's not the same thing. So care in expression, there is actually, it requires a great deal of care to be both precise and informal at the same time. So everything that we've discussed is about large samples. If the sample size is large, then the empirical distribution of a random sample, the word random is crucial. If you had a non-random sample, none of what we're saying is true. Resembles the distribution of the population, and now, with high probability. There is a small chance that if you sample 5,000 times from our table, 5,000 times you get that one that had 580 minutes of delay. That is not likely, but it's there, right? So everything that we're saying happens with high probability, and much of inference has to do with accounting for the small probability that you're off. Okay, time to play some games. That is a roulette wheel and a roulette table, and we are going to gamble, and we're going to see if we make money. All right, so here is how roulette works. This is a wheel, and you can see there are pockets around it. There are 38 pockets. 2 of them are green, that one and that one. And the remaining 36 are evenly divided, 18 red, 18 black. Okay. This wheel is spun, there's a little spindle, and there's a little ball inside. And when you spin the wheel, that ball ricochets around the sides of the wheel. And when the wheel comes to rest, the ball ends up in one of those pockets. That pocket is called the winning pocket. You are allowed to place bets on which pocket will be the winning pocket. And so this is what is called a roulette table, and the bets are laid out here. The first bet we're going to start with is something very simple, a bet on red. So bet on red just says that you are betting that the ball will land in a red pocket at the end. All with me? Okay. So what's your chance of winning? 38 pockets total. How many red? 18, right? Because there are 2 of the 38 are green. Then the 36 are half and half red and black. So 18 and 38. Yep? All right. The bet pays 1-to-1. It pays even money. Here is what this means. And this is an image you need to have very firmly in your mind. I'm trying to turn you off playing these games. Okay. So here is the image. You will walk up to this table, And there is a person called a croupier, and this person collects all the money and deals with running the bet and so on. And you are a big spender, you will walk up and you will say, okay, I am going to bet $1 on red. And so the croupier will look at you, and the first thing, before anything has happened, that you have to do is you have to hand over your dollar. Nothing has happened and already you're out of money. Right? So you hand over your dollar. Okay? Now the wheel, other people place bets, different bets and so on. Now the wheel is going to be spun. So the wheel is spun. This is the big event. There is often some, blonde lady involved, and, people are rubbing their rabbit's foot and going, let's go, baby, and all of this nonsense. Right? But what's happening is a wheel is spinning and a ball is ricocheting around. And at the end, that ball comes to rest in one of the pockets. Remember, you're out $1, yes, already. If that ball lands in a green or black pocket, bye-bye dollar. You never see it again. You just walk away. Okay. If the ball lands in a red pocket, then you get your dollar back. Are those winnings? They're not. That was your dollar in the first place, plus one more. So your net winning is $1. So when you say the bet pays 1 to 1, the net winning is 1 and the net loss is 1 on a single dollar bet. Okay? We'll do a something else to 1 bet in a moment. All clear? That's the game. All right. Now remind me what the chance was that you win your bet. 18 in 38. Is that a half? It is not a half. Is that more than a half? No. It is less than a half. You have less than even chance of winning, and the bet pays even money. Please remember, casinos are not charities. Right? All the bets are set up in ways that do not favor you. Okay, shall we play? I think we should play. Okay, so let me just check that I ran this. Yes. So this is our representation of the roulette wheel. There are 38 rows, one for each pocket, and each one is annotated with its color. This is just something that we created, and it will be available to you. That's the wheel. And what we're going to do is we're going to bet on red. And so here is a function that simply says what you win if you bet on red for each of these colors. So it takes a color as an argument. If the color is red, it returns +1, and for anything else, it returns -1. Does that seem like a reasonable function to be using? Yes? So here, you will have the first part. The bet pays something to 1. That's the first something. That's your net winnings, and this is your loss on a dollar bet. Okay, so we define this function. And now what we do is what I'm going to do is I'm going to apply the function to this column right here. Right? And just see what I would win for each of these different pockets. Nothing is random yet. So we create a new table called wheel, which has another column, and that's applying our new function to the color column, and bets looks like this. And so now you have, for every pocket, you have the amount you would win, and you can see wherever it's red, it's +1, and for everything else, it's -1. All okay? Okay, so far we haven't spun the wheel yet. We have just set up what the bet is going to do. So now it's a good idea to spin the wheel, is it not? Right? And so by now you know that I don't know if you know, actually. I'm going to spin the wheel a lot of times. What did I decide to use, 200 times? Yeah. I'm going to spin the wheel a lot of times, and I'm going to bet on red every single time, right? And a lot of people are thinking, well, I'd never do that. No, you wouldn't do that. But it is not difficult to imagine 200 separate idiots all doing this. That's what we're doing, right? Casinos are a volume business. They rely on mass stupidity. Okay, so we are going to play this game 200 times and see what happens. And so I'm doing this once. So I am going to, from this table, sample at random with replacement. It's a roulette wheel, the same 38 pockets every time. I'm going to sample 200 times. I'm going to get a set of outcomes called spins. And then I am going to look at the winnings column of my sample. Yep. And I'm going to add it up. Does that seem like a good thing to do? Maybe not. Okay, let's see. It's clear what's happening there? That roulette wheel has been spun 200 times, and you have the 200 outcomes. Yep? Now you want to know how much money you make. Should you not be adding this? Yes, all the plus ones and minus ones should be added up. And that's what we're doing here. We are taking from the table spins, we are extracting this array, and we are adding up. Right? You lost $12. Okay. So how about we try again? We spin again, okay? Something different. You lost $22. You made $4. You're on a roll. Maybe you should play again. Okay. So you can see we can stand there doing this over and over again, or we can do what? We can write a for loop. We can simulate. This is what we've been learning all this time. Okay, excellent. So for me, this is the number of bets I'm going to make. I've decided on 5,000 repetitions because I just don't want to wait here until the thing cranks. Now, we are going to want to add up the numbers in this in an array and then collect all those winnings. Agreed? Okay, so we start with an empty array, and then for each of 5,000 times, we repeat our code. We spin the wheel 200 times. We create a value, which is the net gain, and then we add that on. We append that to this array right here. And then we draw a histogram. Ready? Okay. So it's chugging. It's chugging. And here we go. I would like you, all histograms, I would like you to look at the horizontal axis first. What number are you looking for? 0. 0 is where you break even. Is that in the center of the histogram? No. If you look at the chance that you make money, that is the stuff to the right of 0. That's the area to the right of 0. Does that area look like a half to you? No. No, there is quite considerable chance that you lose money, and that is why the casinos are in business. Because the big fraction of those 200 people are going to lose money. Right? And when gamblers lose money, casinos make money. So we're going to stop now. On Friday, we're going to compare this with other bets because people are saying, but I'm going to use this strategy. Okay. And then we're going to start to do some estimation.